So far in chapter 6, we have been working with element proofs or element method proofs. In this section, 6.3, we will be working with what's called algebraic proofs. So in other terms, we're going to be using the table from section 6.2, the one with the commutative law, associative law, distributive law, and so on and so forth, to build proofs where we show that certain equalities hold. So let me show you how we're going to be doing that in this section. And also what we're going to be doing in this section is showing what a disproof looks like, basically to show that something is false. Okay, so there are two styles of thinking when you're thinking about these problems that we're going to be doing right here. There's a pessimist approach and there's an optimistic approach. The optimist approach basically assumes that this is true and you try to prove it, whereas the pessimist approach, basically you're thinking that this is going to be false, let me find a counterexample, and if you can't find a counterexample, you're going to go ahead and prove it, basically. Okay, so the question here in example 1 is this property true or false? And the way I'm going to do it is by building a Venn diagram and kind of testing whether the left hand side will equal to the right hand side. So to start off, I'm going to build 3 little circles in my universe. So the little box represents the universe. Usually we call that capital U. And each of the circles is going to contain numbers. So like, for example, I'm going to go 1, 2, 3, 4, 5, 6, and then 7, and then 8 is on the outside. So basically the set A, according to this little graph, is the set of 1, 2, 4, and 5, whereas the set B is going to be the set of numbers 2, 3, 5, and 6, and so on. C is going to be 4, 5, 6, and 7. So with this in mind, I'm going to go ahead and research what the left-hand side of this equation looks like and what the right-hand side will look like. So first, for the left-hand side. So for the left-hand side, I'm going to do the following. I'm going to calculate the A minus B first, and then I'm going to calculate the B minus C, and I'm going to do the union of the two afterwards. So after I find what each one of them is going to be alone, I'm going to do A minus B union B minus C. Okay, so A minus B. This is basically all the elements in A that don't already exist in B. So these are the numbers 1 and 4. And this is a set, so keep the set builder notation around it. What about B minus C? These are all the elements of B that are not already in C. So there's the number 2 and there's the number 3. Now the union of those two together is going to be the set 1, 2, 3, and 4. Okay, so I'm going to put that on the back burner for a second. This represents the left-hand side of my problem. Now what about the right-hand side? The right-hand side, this is second bullet, right-hand side is going to be the A minus C. Okay, the right-hand side is pretty much this right here. Okay, so A minus C is going to represent all the numbers in A that are not already in C. And you can see in the little bubble, the A circle contains 1, 2, 4, 5. 4, 5 are shared in the pink bubble. So the answer is going to be, in this case, 1, 2. And what I want to do right now is point your attention to the fact that these two boxes are not equal. Okay, so note that the left-hand side is not equal to the right-hand side. Okay, so to summarize, is the statement up here true or false? The answer is it's false. Okay, so is the property true? Nope, it is actually false. And this is what we would call a proof by counterexample. So this is a proof by counterexample. And that's the end of the problem.